Okay, well, welcome everyone once again. This is the second lecture of the course Infinity Categories and Homological Algebra. And the plan for today is as follows. So the main idea today is to give an informal, with emphasis on informal, introduction to infinity categories. And then, if time permits, we'll speak about a specific kind of categories / infinity categories that will be important for the first course using infinity categories in La Plata. So let's start with some motivation. Okay, so one slogan I want to make clear is oftentimes, say, in algebraic topology, we care about spaces, maps, diagrams, and commutativity up to homotopy. I will give a concrete example of this phenomenon in a second, but kind of the idea is to keep track of all adherence data. It's okay if this sentence has no meaning as of yet, because the idea for today will be to make this meaningful. So I'll give some examples of what I mean by coherence data and what sort of object allows us to keep track of such things. So let's do a concrete example of this motivation trace or something of that sort, which is homotopy pushouts. So say in topological spaces, pushouts are not invariant under homotopy, are not, say, homotopy invariant, let's say that way. And I will tell you what this means with a specific example of a pushout, which is as follows. Say we can construct the two-sphere by gluing together two disks at the edges, right? Both edges are a circle. If we take two disks, inflate them a bit, and solve them, I guess. At the edges, then this circle now becomes the equator, and we get a two-sphere. So we have a pushout like this. Now, both of these disks are contractible, so they can be collapsed to a point. But if we do this and then consider the new diagram and use our definition of pushout, then this is just gluing 2 points one to the other, so it's a point. So the end result is a point, and this is definitely not the two-sphere. Right? I mean, the two-sphere has a two-dimensional hole, and this is a point, as it's flat. So this construction of taking pushouts, at least in some naive way, because I'm not being entirely specific, is not invariant under homotopy. One can fix this let me just do it in the example by considering this notion of homology pushouts. So what you instead do is you take, for example, in this case, it's S1. You take a product with the interval, and then you glue one of the edges, which is a circle, to one of the points, and the other copy of the circle, which is another of the edges of the cylinder, to the other point. So this is more or less something of this shape, which again, if you pump air or something, you inflate it enough, does give the correct answer. Okay, but I'm sweeping a lot of details under the rug. And so these diagrams now should have some sort of homotopy coherence property. They should commute up to homotopy and be universal in some sense. And then you start the original diagram of just the objects and the maps to keep track of. And that is kind of what we want to do in a general sense. So we want a model for categories in which you have maps. You also have like homotopies between them, and then also homotopies between those, and so on. And we can do this in several ways. Let me, before doing an informal presentation of how one could go about this, I'll say one formal thing and a bunch of references you can use to read more about this and actually look at a concrete definition. So one possible model for infinity categories are quasi-categories. Which are a special kind of simplicial set. So one of the key points of why I'm not defining infinity categories today and rather doing an axiomatic, so-called axiomatic or informal presentation, is that I would have to define simplicial sets and all sorts of conditions to just give the definition, and this would take a lot of time, which we unfortunately do not have. But if you do know some things about simplicial sets, then these are just a special kind of simplicial set. And you do or you don't, but you can most definitely check out some of these references that I'm about to write down. So there's I think this is on the archive. I don't know if there's a published version. A short course on infinity categories by Groth. And then an axiomatic approach, which inspired this presentation, is also chapter 2 of Introduction to Stable Homotopy Theory. By Knussen. And then textbooks on the subject, which are a bit more comprehensive. They take more detail to define things. This is an overview, and in this, you use them in an axiomatic approach to other things. I'll just write them down. You can also, if I'm going too fast with this, you can see it in YouTube. So you have higher algebra and higher theory by Lurie. And then also, let me just write it here. Higher categories and homotopical algebra. By Szynski. Okay, so these are the references. You can look at a more precise definition there. You can also contact me if you want me to make precise any of the things that I will say today. Right. So let's start. So as I said, we want to build a category in which we have objects, morphisms, and then some notion of homotopy, and then homotopies within homotopies, and so on. So we should have objects. We should have morphisms. And then we should have inductively n+1 morphisms between n morphisms. I will typically denote this if my n is greater or equal than 1, then this is an n+1 morphism, so it's greater than 2, greater or equal than 2. I will denote it by this, like this. Okay, so we should have objects, morphisms, morphisms between morphisms, and so on and so forth. And they should satisfy a bunch of things that I've written in a specific order. So let me look at it. Right, so there should exist notions of composition and identity which are associative up to homotopy. Okay, and we can define that two morphisms are homotopic if there exists a morphism in a higher level connecting them. Right, I will make this more concrete in an example in a bit. But if that's your notion of homotopy, then for example, you no longer care about morphisms that are isomorphisms, but that have some sort of inverse up to homotopy. You don't care about morphisms that satisfy conditions such as these ones, where this symbol means there's a two morphism connecting the compositions to their respective identities. Okay? Okay, let's proceed by example. So let me tell you just one thing that does fit this structure. So say X is a space. Then we have an infinity category called the fundamental infinity groupoid. So the objects are points in X. Okay? Here's an object. The one morphisms, which unless specified, I will just call morphisms, are paths. So this, for example, is a morphism between 2 points. Okay, and the two morphisms are homotopes. So you have another path, say, gamma and gamma prime. Then morphisms between those are forms of deforming one path into the other continuously. I'll just do this. Okay. Now you can go further. Three morphisms are homotopes between homotopes, and so on. But I want to stop here and emphasize that up to here, you already started to see this associativity and identity up to homotopy. Precisely because, for example, you can always, if you have a path, you can always go in the reverse direction. And this is always homotopic to a constant path, not equal. And likewise for composition, if you have three paths, one of the first things you prove when you're defining, say, the fundamental group is that this is associative up to homotopy. So this kind of phenomenon is what we're trying to capture in a very simplistic way. We're trying to pass from equality to coherence data or to homotopies. And in particular, when we had equality, well, two things, being equal is a property. Two things are either equal or they're not. But now equality becomes structure. So to say that these two are in some sense the same, you have to provide a two morphism exhibiting that they're the same. So now each time you want to say two things are equal up to some notion, you have to carry a bunch of structure. And one of the goals of this theory is to make this organized in a way that you can prove theorems. And also capture phenomena you're interested in the first place. Okay, another example, it's of a similar vein, but more global, so to speak. It's an from anima, meaning soul in Latin, is the category of spaces up to homotopy. So here, objects are spaces. Morphisms are continuous maps. Two morphisms are homotopies, and so on. Then you have homotopies between homotopies. Okay. Okay, and yeah, we have a question, I think, here.
The composition is very like unique homotopy that is clear, but it's like anima is age top, but with more information, right? There, like the way that we will formally.
Yeah, so let me repeat the question because I think only my mic captures the audio. So the question was comparing this anima versus taking topological spaces up to homotopy as a one category. So it's the category of topological spaces, but the homes are continuous functions up to homotopy. And yeah, the answer is yes. In some sense, what you're trying to do here is you're trying to invert homotopy equivalences, and you can also do this in infinity categories. And this too will be related. But that's, I think, all I want to say about it now. But yeah, you should, if you've seen H-top, this should make you think about it. I think that's the best I can answer as of now. Okay, and then another example which is very important is that if you have C a one category, then you can view it as an infinity category. With all hieromorphisms being identities. So if you don't have hieromorphisms, then you just have the definition of a category. And this reminds me, I think I forgot an extremely important point, which this can be captured by the camera, right? Okay. Something one should add to the quote unquote definition of infinity category, so please do not forget this. So we require all n-morphisms for n greater than 1 to be invertible. So this is what happened for spaces. Of course, not every continuous map is a homotopy equivalence, but once you have a homotopy between maps, you can also do it in the reverse order. And this is an inverse up to a 3 morphism. So from 2 onwards, these are always invertible. The only non-invertible phenomena can happen at level 1. And in fact, if all of your morphisms are invertible, including the one morphisms, then your infinity category will be of this form. It will come from a space, so to speak. So this covers both things coming from the homotopy theory of spaces, one categories, and some things in between. This is one of the ideas of the theory, is to encapsulate both phenomena from one category theory and homotopy theory. But yeah, so this was an extremely important point that I forgot in my list. Let me write it down here. Sorry, the question was, what was I saying in the remark? So I want to write it here. So the remark is, if C is an infinity category, and in addition, one morphisms are invertible, then it's equivalent in a sense that I haven't defined, but I will, to the infinity groupoid of a space. So what I'm saying is that these are actually called infinity groupoids because everything is invertible, and these come from the homotopy theory of spaces. On the other hand, you can also consider one categories, so you get one category theory also included into the theory, and a mix of both things, and you want to capture both of these phenomena. That was my point. But also to emphasize that for higher morphisms, we require them to be invertible. Okay, I missed that in my original list of what an infinity category should be. And I'm also now being very specific about composing morphisms to n morphisms could be composed in various ways. For example, let me just say this. If you're familiar with natural transformations, you can compose vertically and horizontally. So one should also make precise what composing means in several ways. One can do that once you have a concrete definition, but I'm not doing that now. I'm just pointing out that if one wants to do that, you have to be careful. Okay. Right. So my point for today, besides this idea, is that at least if you've never seen, say, one category before, and you're seeing for the first time on Monday, then this is quite a jump in complexity. But I'm going to try to convince you that you can try to see things as if they were one categories with this moral of the story that you have coherence data going on. So this is the main point I want to stress for the rest of the lecture. Let me tell you some facts that infinity categories satisfy that will make you, that will make it able to do whatever you were doing with one categories in the previous lecture, but with infinity categories, okay? So I don't want to abuse of the word axiomatic, but this is of an axiomatic spirit. So, some facts about infinity categories. Right. So one, if you have an infinity category and two objects, then there is a space of morphisms between them. I abbreviate space by it belongs to anima. The infinity category of spaces up to homology. So what I'm saying is this encodes one morphisms between x and y and two morphisms and so on. If you capture all of this data, the ones I go from x to y, you end up having a space. So it's like if you have the fundamental groupoid of a space and you fix two specific points, then you have all paths going from P to Q, all homologies between paths going from P to Q, all homologies between homologies between paths going from P to Q, and so on. Okay, and this can be built into a space. Okay. Yes, I mean topological space, although to be safe, I could just say CW complex, if that helps. Okay. Okay, another thing is that if you have two infinity categories, just like with one category, there is another infinity category of functors between C and D. And so its objects I call functors. It's a definition, if you will, / notation. And its morphisms are natural transformations. Okay, so if you at least believe that given C and D, there is some way to encode functors, so things that respect objects, compositions up to homotopy, compositions of homotopys, and so on in a coherent way, I call functors the objects of such a thing, and natural transformations the morphisms of such a thing. Okay, of course, I'm not saying what this is, I'm just saying it exists. Right. Sorry, could you say that again? Condition one. Okay. So the question was, why is it important that between two objects, instead of having a set of morphisms, you have a space? What I'm saying is that this is sort of trying to encapsulate the fact that, so points here are morphisms. A homotopy between two morphisms you can think of as a path in this space. Okay? Because you're trying to consider maps, homotopies between maps, just like in topological spaces. In topological spaces, at least with some hypothesis, you can think of a homotopy between x and y as a path I in the space of continuous functions from x to y. Okay? So that space is trying to encode that. Its points are the morphisms we had in one categorical style. Paths between them are homotopies, and then homotopies between paths are two homotopies, and so on.
I have a question. Said that I'm the category of space, like up to homotopy. But there are morphisms between morphisms to be inverted by the infinity category condition. Right?
Yeah, so the question was, yeah, animus the infinite category of spaces up to homotopy. And then?
But the two morphisms, the infinite category C, should be inverted, right?
Yes, so yeah, in C, two morphisms are invertible, but two morphisms here would be homotopies between homotopies, right?
All right.
And you can always reverse homotopies.
Okay.
As in something special that happens, say you get a sort of thing like this drawing. Paths you can always go in the reverse order. So in spaces you're okay, I think.
Isn't true that in home C X Y every one more? That is true.
I mean, sorry, this is a space.
Right.
Maybe that's the confusion.
Yes.
Yeah. Home CXY is a space, a topological space. Or at least, yeah, up to homotopy. It's a homotopy type of a topological space. Okay. Another fact is that infinity categories form an infinity category. I'll leave it there, but okay. And well, another fact that you might even expect if you want things to be resembling one category is that if you have an infinity category, there is a functor encoding all of these hom spaces. I always forget where the op should be. I think it's here. So this is very straightforward. If you replace anima by sets and C by a one category, this is very straightforward to do for one categories. And it's actually quite difficult to construct for infinity categories. So another slogan one can make is, so most things remain the same, but the proofs are much more involved. Okay, but why am I telling you this? Because if you believe all of these things, then you can definitely believe that you can define adjunctions. So if I have a pair of functors, f and g, between two infinity categories, I say that they're adjoint if the following happens. So I have hom d fc comma d has to be, say, homotopy equivalent to hom c C comma G of D in a coherent way. But this we can actually formalize with what we have already said. So this means that this is a natural isomorphism. So what I'm saying is that these two functors are isomorphic in this infinity category. Functors from C up times D to anima. So it's exactly the same definition as for one categories. So at least if you believe that you can make sense of this and of functors and of an infinity category in which functors are objects and isomorphisms between them are natural isomorphisms, then you can most definitely believe you can define adjunctions. And if you can define adjunctions, then you can define co-limits in a very similar fashion. So that was 5, right? So likewise, we can define co-limits. So a co-limit of a certain functor from I to C is C and C, and the natural isomorphism from C Cx, where C is fixed and X is the variable, and natural transformation, so but in the functor category, between F and the constants diagram X. So if you replace X by blank, you get two functors with the same domain and codomain. And I'm saying that if these two are equivalent in another functor category, then C is a co-limit. But again, my point is just that once you believe a couple of facts, if you are seeing this for the first time, then you can extrapolate many things, at least heuristically, from whatever you know about one category. Okay. Right. Let's see how we're doing with time. Okay. Right. So for example, let me tell you one advantage of having done all this is that, say, in this infinity category anima, co-limits model, in this sense, homotopy co-limits. Because you're now keeping track of the homotopies. So you can formalize that definition by using the notion of co-limit for infinity categories. And in a one category, this is a bit absurd in the way I'm writing it, but co-limit is co-limit. So what I'm saying is that if you view a one category as an infinity category, then this notion of co-limit is really the same as the one you had before. Okay. Okay, and one other thing is that, as I said, many results just because I want to be careful and not say all results. From one category theory hold, like the Yoneda lemma, for example. But the proofs are much more involved. So the existence of this home functor that I described before, or the Yoneda lemma, or the fact that a natural transformation is invertible if it's invertible object-wise, or that an equivalence between categories is the same as essentially surjective and fully faithful. So if you've seen any of these things, all of them hold, but the proofs are much harder. Okay. Right. So we have, I think, 15 minutes or so to go. And the other thing I want to talk about is a bit long. So I'm thinking about what we can do. Okay, maybe I'll just say one more thing about this approach to infinity categories and facts about infinity categories in general. And then I'll just give you an intro of the next topic, which I can cover on Friday so that we don't go over time. All right. All right, so another remark is we can view one categories as infinity categories. Now, there's also another procedure if T is an infinity category. We can also consider one category. Which is called the homological category. You see? So the objects stay the same. And then the morphisms lucky for us, we only have to specify one morphisms this time. All right, so these are one morphisms up to homotopy, okay? Whereas I was saying before, you say two one morphisms are homotopic if you have some two morphism connecting them. So this actually gets you a one category, okay? Which of course discards most of the coherence, okay? But what happens if I plug the examples I gave you? Well, if I take the infinity groupoid of a space, then I get the fundamental groupoid of a space, right? Which, if you've seen the fundamental group and not the fundamental groupoid, it's just like the fundamental group, but you haven't chosen a point. It's like a point-free definition of the fundamental group. Okay. Now, if C is a one category, then the homotopy category of C is C. Because homotopies, higher morphisms, are identities. So you can only identify things that were equal to begin with, meaning you just get one morphisms in C, so one morphisms in C. Okay. Right. And then if I consider spaces and maps between them up to homotopy, I should get topological spaces up to homotopy, right? So in some sense, these are very similar on one hand, but actually quite different because you're discarding most of the coherence data and only taking things up to step one. Say. Right. Okay. And in the, say, 10 minutes or so that I have left, now I want to change the subject quite a bit. So let me just emphasize for the millionth time the point. So what we've seen today is that infinity categories are a mixture of one category theory and some aspects of homotopy theory. There are various ways to define them. Most of them are a bit technical for the time we had and we have. So what I'm trying to say is the minimal set of things one can believe so that you can work with infinity categories as if they were one categories. Of course, much is lost in this process, and I apologize if something has not been clear. Please do ask questions. And then, well, what I want to do now is speak about a specific family of infinity categories, but again, following the slogan, if you haven't picked up all of the things I said, you can believe they're one categories for a moment, which will be quite important in some of the courses that you'll see. And they are, in some sense, categories that are generated by small objects, whatever that means. So let's try to at least give an idea of what that means in 9 minutes. Okay, so I'll tell you two facts, which imply that two categories are presentable. Of course, we haven't defined what presentable is, but that's kind of the idea to first do this. So say a set X is a union of its finite subsets. Right? Any set. So whatever notion of small we're about to define, it better say that finite sets are small. And if you allow to have finite sets and some procedure of gluing, like unions, right? Which is like take a disjoint union and then glue things that you're counting twice. Then what you're saying is that you can build any set by gluing small sets, in some sense, finite sets. Okay? Let me give you another example. So let R be a ring. Finitely presented module or let's say, sorry for this, but an R module, M is finally presented if there exists a short exact sequence of the form R to the N, R to the M, M, 0. So what I'm saying is it's definitely finally generated because I have an epimorphism onto M from R to the N, but also the kernel is finally generated. The kernel of this is the image of this one. So it's also finally generated, right? So finally many generators and also finally many relations. Okay? And now a non-trivial fact, much harder than the one for sets, is any module is a co-limit of finally presentable modules. Okay. So if I were saying just finally generated, then you can do a very similar argument like for sets. You just take a union of things, of finally generated submodules of M, and that's it. But here, I really mean co-limit, so I really need to glue without necessarily restricting myself to a union, and I need finally presented. But I don't care so much about the details. I just want the analogy, which is in both cases, all the objects can be generated by gluing, so about co-limits of some sort of notion of small objects, of compact objects is what we'll define. Okay. Okay. So I guess with the time that I have, it's best to just, yeah, I know. Here in the audience, they're reminding me that I have 5 minutes. I think it's best to maybe stop early. I'll give you the definition, and it will have 2 or 3 words that I haven't defined, and I do that next time. But it will resemble that phenomenon. Okay. If I do it the other way around, I will start by defining things I haven't motivated, and I think that's much worse for an ending. So we're not starting in the right foot, possibly. I haven't said anything about this. Okay. Let lambda be some cardinal with some conditions. Then a category C is presentable if 1, it has all co-limits, and 2, there exists a set S of compact objects such that every object in C is a filtering co-limit of objects in S. Filtered, filtering, maybe filtered. I think I might be wrong here, but I think both are in use, but just to be safe. A cardinal. Just, yeah, maybe Yeah, maybe wait, just give me 1 second. I'll just go over the definition because I have a minute left, and we can go over that in the question section. So let lambda be some cardinal with a condition I haven't explained. Then C is presentable for some size, some fixed size. If you can glue all you want, so you have all co-limits, and you also have a set of compact objects, which are in some sense small, bounded by this cardinal in some sense, and you can get all the others by gluing, but you can't glue too many objects. That is also in some sense controlled. All of these words I haven't defined, and I don't have to do it. I don't have time to do it now, but I think we can pick up from that next time. So yeah, that's all for today. Maybe let's first say if there are any questions in the chat and so on. Okay, here somebody asks, what's the definition of compact? Yeah, so right, so that there's a comment from Dave. So maybe a note from my side, he says, any presentable one category is a presentable infinity category. So if you came in knowing what a presentable one category was, you now know some presentable infinity categories. Yeah, and that is exactly my point, that if you see this definition, of course, I haven't defined all the terms, but they will all depend on phrases like co-limit, functor, category, and by what we have discussed before, if you just write infinity next to most things, you can get away with the same definition and up to some point also same theorems. So yeah, so the examples I gave will actually give rise to presentable infinity categories. And there's another comment saying another class of examples comes from equipping categories with combinatorial model structures. This gives you all presentable infinity categories. So yeah, I have no comment on that today. Right. Any other questions? Okay, so Willie here asks, what's a lambda filtered co-limit? That means it's a co-limit index in a lambda filtered category, and that's that each time you have a diagram, let's say D is lambda filtered, if each time you have a diagram and this has less than lambda objects, then it admits a cone. If D is a poset, then that's the same as saying that each subset of cardinality less than lambda has an upper bound. And this is, of course, maybe the intuition one has in mind typically, but you really need to define it for categories in general. And to answer the question of whether I can define compact, so to define compact, I need to define filter co-limits. To define filter co-limits, I need to define what a filter category is, and I think we would go a bit over time. But I mean, yeah, I know I have done it, but in an organized way, I mean, it will take me some time. I think it's best to approach it with a fresh mind on Friday, because I've seen a lot of things today. So I'll leave you hanging.